All right, now we get to move into fun stuff, gas laws. But before we get too much further, I just wanted to quickly differentiate what makes a law a law. So a law is something that summarizes a large body of data but provides no explanation. If you think about what provides explanations, right? An explanation is provided by a theory. In this case, the theory that kind of explains what's going on with gases is the kinetic molecular theory, which is what we talked about previously. But I just wanted to get into the main difference. A law often has a math formula associated with it. So for these next few sections, we're going to be dealing with some basic math formulas, but they're really not too bad. You can do them with algebra. So let's think about some important math variables that we may need to use. So let's make a list. With gases. All right, so the first variable we need to consider, and I put math in here just because we know we're going to be dealing with a formula. The first variable we need to consider is pressure. And pressure, if we think about it, is often expressed relative to atmospheric pressure. And you might be wondering, all right, well, what in the heck is atmospheric measure and how do we measure it? Well, atmospheric pressure is basically the pressure from all of the gas above you all the way out to kind of the edge of space. So that volume of gas or that column of gas directly above you is essentially applying some sort of weight on top of you. That's the pressure of our atmosphere. So how do we measure atmospheric pressure if we're weathermen, for example? Well, there's a cool tool you can use called a barometer. And a barometer looks like this if you actually look at one in person. But the way it works is on the inside of this tube here, you fill it 100% full with liquid mercury. And then down here on the end, you kind of cover it with your thumb or a cork. Really, you should use a cork, not your thumb, because mercury is bad for you. And then you put it into a dish of mercury at the bottom, and you release that cork. And what you'll notice is up at the top, you get this kind of drop in here. And on the inside, you've got a vacuum, meaning no gases are really present in there. Okay, so then the question is, well, what is going on? Well, over here, you've got atmospheric pressure pushing down, right? And what we can do is we can measure the distance that the mercury is held up. Basically, we're measuring atmospheric pressure relative to the vacuum that's being created, which is kind of a really long-winded way of saying we can measure our atmospheric pressure using a barometer. So this is just a mercury barometer. It's kind of neat. The reason they use mercury instead of water is mercury allows this to be done on a scale that is, readily accessible for most scientists. If we used water in a similar fashion, I think it would have to be somewhere like 30 feet tall. It's just not very practical to make a water barometer. All right, so let's take a look at other forms of pressure, because we don't just use atmospheric pressure as chemists. In fact, there's a number of them that we use. So let's go ahead and take a look at all the different pressure units. And like I said, we've got atmosphere right here. So the atmosphere around us is kind of the standard that we relate everything to. However, we've got other units as well. In particular, we've got the unit of torr. So torr is another unit of pressure for gas. And we know that 760 torr is equal to 1 atmosphere. So we can actually use this as a unit conversion. So use for unit conversions. So if I give you a value in torr, you should be able to convert it to ATM. Same thing with millimeters of mercury. you could say, well, this is actually how we measured our atmosphere, right? So let's go back up to our barometer. When they measured this height right here for normal atmospheric pressure, this can be measured to be 760 centimeters, or sorry, millimeters, which is kind of neat, right? So we can convert between atmospheres and millimeters of mercury. It's kind of a unique thing. We can also go from pounds per square inch to atmosphere by using this unit conversion. It's just another unit conversion we can refer to. We can look at another unit of pressure called bar, and we've got some unit conversions for bar. And then we've got kilopascal as well, and we've got our last unit conversion down here. You can see that over on the right-hand side, these are each used for different circumstances. So atmosphere, torrs, millimeters of mercury, and kilopascals are used in gas laws. We're primarily going to be using these top three. However, if you're dealing with, let's say, compressed gases in a hospital, you might see those tanks measured in PSI. And then if you think about meteorology, oftentimes you're expressing pressure in bar. It all just depends on your subfield. So we might be using these interchangeably. But let's go ahead and just do a quick unit conversion just for fun to practice. And the other day I was pumping up my bike tire and it was 115 PSI. My question is, what would that be in atmospheres? All right, so we could say, well, up here, one ATM is 14.7 PSI. So we could say, well, let's just set this up as a unit conversion. So 115 PSI. We want to cancel out PSI. So I'll put that on the bottom. And our goal is to get to atmosphere, so I'll put that on top. This way, our PSI units cancel, and we're left with our atmosphere units. But up here, you can see 1 is put with the atmosphere unit. And then over here, 14.7 is put with the PSI unit. So I'll put 14.7 down below with our PSI. And now we can do our quick and simple math, and we want only 3 sig figs. So I would calculate this to be 7.82 atmospheres, meaning the pressure on the inside of my bike tire is almost 8 times the pressure of our normal atmosphere. It's kind of weird to think about it that way, huh? This is for a road bike. If you're in a mountain bike tire, you're typically around like 30 to 45 PSI. All right, so that's one big variable that we need to consider, is we always need to look at the pressure of gases, because we know that gases are compressible. All right, let's move on to the next variable. Next variable is temperature. And temperature is usually expressed in Kelvin. And it's kind of weird to think about, but Kelvin is a better scale for measuring gases. So 0 degrees Kelvin is equal to absolute 0. And absolute 0 is another way of saying that we have no kinetic energy, meaning molecular motion stops. It's really kind of an impractical thing, but more of a theoretical thing, that what would the temperature be if molecular motion were to stop? We can get things really close to absolute 0, but it's more of an idea than an in practice thing. All right, so how do we do these conversions? Well, we can do it a few different ways, and in fact, we talked about this briefly earlier this quarter. We said that Kelvin is the same thing as degrees Celsius plus 273. If you want to do the opposite one, you can say, well, Celsius is going to be Kelvin minus 273. So again, we may need to use this to convert between Celsius and Kelvin, or vice versa, depending on the situation. And then the last variable that we're going to look at is just volume. And the volume that we typically use in these situations is going to be liters. So it's typically measured in liters. There's not a whole lot else to say about that variable besides it's just measured in liters. We don't do quarts or gallons or things like that. We stick with our scientific units. All right, so let's take a look at the various gas laws. All right. And there's going to be a number of them, but we're going to focus on two main ones in this video, and then we'll do a combined version of both of them at the end. So the first one is Boyles Law. Again, named after the chemist that discovered it. But the key thing with Boyles Law is that it assumes constant temp. All right, so instead of looking at temperature, they're saying, let's just look at pressure and volume. All right, so one thing he noticed is if pressure goes up, meaning you apply more and more pressure on a gas, then volume goes down. Another way of defining this is that these are inversely related. All right, it kind of makes common sense. In fact, I wish I were a chemist back then. Sometimes you look at these laws and you're like, well, yeah, no kidding. How did you get this named after you? But anyways, the formula for this is pretty straightforward. We've got two different ways we can express it. We can say pressure equals little k, not a capital K. In fact, let me exaggerate that even more. Little k over V. So P is pressure, V is volume, and then K is a experimentally determined constant. All right, so this is the math formula for Boyles Law. It's pretty straightforward. But again, it gets back to this main idea that if pressure goes up, volume goes down. Conversely, if pressure goes down, volume should go up, right? But now we can express this in a mathematical formula. But in order to do that, we also need an experimentally determined constant. This essentially just allows us to define the relationship a bit better. Okay, so let's go to number 2, the second gas law. So the second gas law is again named after the chemist that discovered it. It's named Charles's law. Okay, and this time he looked at something different. He assumed constant pressure. Okay, so now we're just looking at temperature and volume. So what he noticed was if temp goes up, then volume goes up. All right, so it's no longer inversely related, right? In fact, these are correlated. All right, so this was an observation, and he noticed that again you could fit this to a law where he said, well, if volume goes up, then temperature should go up. But again, we need some sort of constant in here. So again, we're going to do a little k, but we're going to do 2 hash marks up here just to differentiate this constant down here from this constant up here. They're not the same, right? They are each defined separately. So again, we can just say, well, V is volume, not velocity. K is an experimental constant. And T is temp. And it's important to remember that it's going to be temp in Kelvin, not Celsius. So this was the whole idea behind Charles's law. Again, pretty basic, similar idea to Boyle's law, where they just took some simple observations and were able to model it with a math formula. All right, you might be thinking, well, in the first one, he assumed constant temperature, but then looked at pressure and volume. And in the second one, he said assume constant pressure, and then he looked at temp and volume. Really, it's the same 3 variables, so isn't there a way to combine them? And the answer is absolutely. So the last one we're going to look at in this video is called the combined gas law. It takes the two laws we just looked at and it smushes them together. And the easiest way to do this is just to say, all right, so pressure and volume over temperature is going to be equal to a new constant, which I'll define as K with 3 hash marks. Again, this experimental constant is going to be different than what we found up above. Okay, so let's again define this. So T is temp in Kelvin. K is an experimental constant. V is volume. And P is pressure. All right, so this is the combined gas law, and there's actually a number of different things you can do with this. So I'll show you a neat trick. All right, one of the cool tricks you can do with this is that, sorry, let me go back up here. This experimental constant is going to hold true for a given gas. Okay, and this can be used in my cool trick that again is discussed in your book. So basically it says if that's true for a given gas, not GAG, we can compare a gas before and after a change. So what I can do is I can say, well, pressure initial, PI, times volume initial over temperature initial is going to be equal to pressure final times volume final over temperature final. Because each of these, whether it's before or after, is going to be equal to the same experimental constant. All right, so you can use this for before and after situations. So useful to compare before and after changes. And I'll just make a little note here that I is initial, because I know sometimes students will forget this, and F equals final. Okay, so let's do a practice problem, and then we'll call it good here. So practice. Let's consider a steel cylinder, and this is actually a problem I pulled from the book. So a steel cylinder will burst, sorry, that should be a U, above 10,000 psi. So we're doing a compressed gas, that's why we're using the PSI unit. All right, let's consider this. If it was filled to 2,500 psi, at 20 degrees Celsius, but left in the sun and reaches 100 degrees Celsius, will it burst? So you can imagine if you're working in, let's say, a shipping industry where you're transporting oxygen gases to a hospital, this might be something you have to consider, right? So let's go ahead and do this, and we'll say that VI times pressure initial PI over TI is going to be equal to volume final times pressure final over temperature final. So we're doing a before and after comparison. But we can make a few assumptions in this situation. So the first thing I would say is the volume of the container we can assume is going to remain the same, right? So we can say that VI is going to equal VF, that the volume is just not going to change much during that process. The steel is just going to basically retain its shape. Yeah, it might move a little bit, but let's just kind of ignore that. Okay, so this allows us to simplify this problem a little bit. we can then say, okay, well, that just means that PI over TI is equal to pressure final over pressure initial. Okay, so now we can start plugging in some numbers. So the initial pressure that we had was 2,500 psi, and we said that this was done at 20 degrees Celsius, but let's try to stick with Kelvin just for practice. So 20 plus 273 would be equal to Kelvin. Really, in this problem doesn't matter, but we're just going to do this as practice. So I'll go ahead and just stick with Kelvin. And this is going to be equal to some new PSI. I'll call this pressure final, or X. Let's just leave it as pressure final. And the temperature at the end is going to be 100 plus 273. All right, so let's solve for pressure final. Okay, if you're familiar with doing cross multiplying, well, we could say, let's multiply these two together. That's what I always was taught to do. And I'd say, well, 2,500 PSI times 100 plus 273. That's going to be those two multiplied together is going to be equal to these two multiplied together, right? I'm not sure how many of you were taught the same way, but this is how I often worked with problems like these. So pressure final times 20 times plus 273, excuse me. Okay, so now we've cross multiplied. Let's try to solve for pressure final now. So pressure final is going to be equal to 2,500 times, we'll just do the math here, 373, shoot, let's keep our units. Sorry about that. Divided by 293 Kelvin. So really, I'm just going ahead and doing the math here. This is 293, and then over here, this is 370. All right. So we can go ahead and solve for our pressure final now, and we could say, well, the pressure final is going to be 3182.59 something PSI. That's what our calculator will spit out. However, we should only have 2 sig figs because we only had 2 sig figs from our 2,500 PSI unit. So that means that our pressure final, if we're following our sig fig rules, would be 3.2 times 10 to the third PSI. This is well below 10,000 PSI, so it will not explode, thank goodness. All right, I hope that helps. There's a lot of good practice problems in the book. I didn't want to make you watch an hour-long video, but I would strongly encourage you to go through and do some of those practice problems on your own. And if you get stuck, let me know or feel free to post on one of the discussion boards. All right, good luck.